Hello again. In this video, we're going to talk about how we graph functions using calculus. So what we're going to do is we're going to use the tools that we learned from section 4.3 to help us graph functions. Now, in a college algebra class, the way we would graph functions is we would create a t-chart where we pick randomly some x values and plug those x values into the function and find their corresponding y values, and then generate a list of ordered pairs. And then we continue to plot those ordered pairs until we start to see a pattern. And then we can graph the function after we see the pattern. Now that we know some things about calculus from section 4.3, we're still going to plot points to help us graph the function, but we're going to be very smart about which points we pick. And so the important points that are really going to help us graph the function are going to be things like the inflection points, and the relative mins and the relative maxes. In addition to that, calculus is going to help us determine where the function is increasing and decreasing, and also where it's concave up and concave down, which will also help us graph the function. Okay, so let me show you an example of how we would use calculus to graph functions. Okay, so let's say we want to graph this particular function. So it's always a good idea to start with the domain of the function just to know which x values you can actually use when you go to create a t-chart. In this case, the domain is all real numbers because this is a third degree polynomial, and you can plug any number x value into this and you'll get a number out. So the domain here is all real numbers. Now, there are a couple of functions or types of functions you should look out for where the domain might be restricted. Those would include rational functions, functions where you're dividing a polynomial by another polynomial. The reason you might have some restrictions there is because you can't divide by 0. Another possible restriction would be if you have square roots in your function, or in fact any even root for a radical, because we can't take the square root of a negative number, or the fourth root of a negative number, or the sixth root of a negative number. Any even radical, you need to make sure that you're taking radicand is greater than or equal to 0. So that's another possible way of restricting a domain. The other function that comes to mind would be logarithmic functions. The domain of a logarithmic function would have to have positive numbers as input values. So that's a possible restriction on the domain of the function as well. So you need to look out for those three types of functions. Those are one of the three more common functions where you're going to get a restriction in your domain. Okay, so we're still going to create a t-chart, like I said. And we're still going to plot a bunch of ordered pairs to help us graph the function. We're going to be very smart about which points we pick. We're going to pick points that we think of as being important. So the intercepts are also certainly important points. So let's go ahead and find the y-intercepts and the y-intercept and the x-intercepts or intercept. Okay, so for the y-intercept, you should just let x be 0. And when you plug 0 into the function, notice that you get 0 out. So your y-intercept happens to be the origin. Okay, but to find the x-intercepts, you just let y value be 0, or in this case, f. So I'm just going to set the function equal to 0. Okay, and of course, you can factor an x out of this, and that's going to leave you with x squared minus 6x plus 9. And then this is going to factor into x minus 3 times x minus 3. Okay, and so that means x would have to either be 0 or 3. Okay, so obviously this is also an x-intercept as well as a y-intercept. But in addition to that, we also have an x-intercept at 3, 0. Okay, now what we're going to do is we're going to try to get as much information as we can from the first derivative of the function. Okay, so let's go ahead and find the derivative, which is 3x squared minus 12x plus 9. Now what we're going to do is we're going to create a sign chart for the first derivative. So the first thing we're going to do is find the critical numbers. And remember, the critical numbers are when the first derivative is either 0 or does not exist. Okay, so let's set this equal to 0. And so you can factor out a 3 here. That's going to leave you with x squared minus 4x plus 9, or plus 3. And then you can just divide by 3 here on both sides. And that's going to leave you with x squared minus 4x plus 3. And that's going to be equal to 0. And then you can factor this into x minus 1 times x minus 3. And so we end up with x is equal to 1 or x is equal to 3. Okay, so those are your critical numbers that you get because the first derivative is 0 at those particular numbers. Now, you also need to check any places where the first derivative does not exist, because those also give you critical numbers. In this case, this exists for all x values since it's a second degree polynomial. So this never happens. Okay, so we only have 2 critical numbers. And now what we're going to do is we're going to create a sign chart for the first derivative, breaking up the number line at the critical numbers. Okay, so the first interval is going to be from minus infinity to 1, and then 1 to 3, and then 3 to infinity. Okay, and then what we're going to do is pick a test point in each of the intervals and plug those test points into the first derivative to see whether the function's increasing or decreasing in those intervals. Okay, so let's use 0 for this test point. So f prime of 0 would give us 9. Of course, remember, if the first derivative is positive, that means the function's increasing. Okay, and so in here, let's just pick 2 for a test point, plug that into the derivative, and it looks like you're going to get 2 squared is 4, so 4 times 3 is 12, and then minus 24, then plus 9. Okay, and that's going to give us negative 12 plus 9, which is negative 3, and so that means the function's decreasing. Okay, and then a test point in here, we could use 4, and then plug that into here, and we get 16 times 3 is 48, minus 4 times 12 is 48, so you're going to subtract the 48, plus 9, so we're just going to get 9 out of this. That means the function's increasing. Okay, so then this is a sign chart for the first derivative. Now, not only does the sign chart for the first derivative tell us where the function's increasing and decreasing, it's also going to tell us where we have relative maximums and relative minimums. So since the function's increasing over here and then decreasing over here, that means we have a relative maximum when x is equal to 1. Then since it's decreasing here and then increasing over here, we have a relative minimum when x is equal to 3. And so those are going to be important points. So I'm going to add those into the t-chart. So we need to know the y value when x is 1, so we can plot that point. And so that means you have to plug 1 into the function to find its y value. And when you plug a 1 into here, you get 1 minus 6 plus 9. And that's going to give you 4. And the reason that's an important point is because it is that's a relative maximum. Okay, we also need to know the y value when x is 3. Now plug a 3 into here, and you get 27 minus, 3 squared is 9. 9 times 6 is 54, so minus 54, plus 9 times 3, which is 27. Okay, and so that's just going to give us 0. And that's an important point because that's a relative minimum. Okay, so that's about all the information we're going to be able to get from the first derivative, the sign chart for the first derivative. It tells us where it's increasing and decreasing, and it also tells us where we have relative maximums and relative minimums. Okay, now let's go to the second derivative. We're going to create a sign chart for the second derivative. Okay, so the second derivative would be 6x minus 12. And then we're going to find the possible inflection points. Okay, and the way we're going to do that is the possible inflection points occur when the second derivative is either 0 or does not exist. Okay, so let's start with when the second derivative is 0. So if you solve this, you're just going to get x is equal to 2, add 12, and then divide by 6. Okay, and then we also have to look at the case when the second derivative does not exist. But it exists for all x values here. That's just a first degree polynomial. And so this never happens. Okay, so we end up with one possible inflection point. Now we do have to check and see if it actually is an inflection point. This is our only candidate for an inflection point. If we have an inflection point, the only place it can occur is at x equal to 2. Now, to find out whether it really is an inflection point, we have to check and see if the function is changing concavity at x equals 2. That's the definition of an inflection point. It's a point on the graph of the function where it changes concavity. Okay, so to do that, we're just going to create a sign chart for the second derivative. And so the first interval we need to look at is from minus infinity to 2, and then 2 to infinity. And then we're just going to pick test points in both of those intervals and plug them into the second derivative. Okay, so a good test point in here might be 0. Now let's plug that into the second derivative, and we get negative 12. And that means the function's concave down. Remember, when the second derivative is negative, it indicates that the function's concave down. Okay, and then let's pick a test point in here like 3 and plug that into the second derivative, and you get 18 minus 12, which is 6. That indicates that the function's concave up. Okay, so you can see that the function is changing concavity right when x is equal to 2, and so this really is an inflection point. And so that's an important point, so we're going to want to know what the y value is. So to do that, of course, make sure you go back to the original function and plug 2 in to get the corresponding y value. Okay, so we got to find f of 2. Okay, so f of 2, we're going to get 2 cubed, which is 8, and then 2 squared, which is 4 times 6, so that's going to give us minus 24. And then 9 times 2 is 18. Okay, so this is going to give us 2, and this is an inflection point. Okay, so then once you've compiled all this information, then you want to go ahead and plot these important points. And then once you plot those important points, you want to go back to your sign chart for the first derivative and follow the chart where it's increasing and decreasing. And then also look at the second derivative to determine what the concavity is. Now you may want to create what I call a summary chart, which combines these two together. So starting at minus infinity, the first place something interesting happens is at 1. And then the next place would be at 2. And then the next place would be 3. And then after 3, nothing else of interest happens. So I call this a summary chart. Now in this interval, it's increasing, but it's also concave down. Now once it gets into this interval, 1 to 2, it starts to decrease. It remains concave down because it's still in this interval. Okay, and then between 2 and 3, you're still decreasing, but now you're in this interval, so that means you're concave up. And then from 3 on up, you're increasing, and then you're concave up. Okay, so this is called a summary chart, and it just combines both of these pieces of information to make it a little bit easier to see what's going on. Okay, now let's go ahead and graph this. So I'm going to make a quick sketch of it. Okay, so we have this point here as an x and y intercept, 0, 0. Then we have an x-intercept at 3, 0. 1, 2, 3, 3 zeros right there. And then at 1, 1, we have a relative maximum. Because it's a relative maximum, it's going to have to look something like this. Okay. Then we have 3, 0, which happens to be an x-intercept as well. That's a relative minimum, so it's going to have to look like that. It's a relative minimum. And then 2, 2 is an inflection point. Which is right there. And there seems to be something wrong with the graph because, let's see, 0, 0, 1, 1, no, 1, 4, sorry, that's what's wrong, 1, 4. So that's up here. It's actually 1, 4. Okay, and then so that's a relative max. Okay, so that makes more sense. Okay, so then you just want to piece all this together. So it's from negative infinity to 1, which is right here. It has to increase. Okay, so it's got to go through this point because that's the x-intercept and the y-intercept. So, and then it's going to be concave down. So it's got to increase, go through that point, but in a concave down fashion. So concave down would look like that, as opposed to concave up, which would look like that. Okay, so it's got to look like this. Okay, and it goes through this point. Okay, so something like that. And then it starts to decrease at between 1 and 2. So here's 1 and 2, right? It's decreasing in here in a concave down fashion. So that's going to look like that. Right? That's decreasing, it's concave down. Okay, and then between 2 and 3, it continues to decrease. So between here and here, it's continuing to decrease. It's now doing it in a concave up fashion. So it's decreasing this whole way. It's concave down in here, and then it changes concavity right at this point. That's why that's an inflection point. 2, 2 is the inflection point. So the concavity changes, and now you have to draw it as concave up. Like that. Okay, and then once it gets to 3, it starts to increase in a concave up fashion. So it looks like that. It's increasing but concave up. And then if you want to just double check this is the location of a relative minimum, like we have over here, and this is the location of a relative maximum. Okay, so that's just a rough sketch of it. Now you could go to Desmos.com and just double check it. And so let's just see a little bit more accurate graph. Okay, so y is equal to x cubed minus 6x squared plus 9x. Okay, and so that's what this graph looks like. Notice this is at 1, 4, the relative maximum. 1, 4 is there. And this is at 3, 0, which is the relative min here. And then you can see, if you look closely, that 2, 2 is an inflection point because it changes from concave down to concave up. Okay, so that's how we use calculus to help us graph functions. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.